Hi everyone, it's Mr. H here, and this video is on elastic potential energy. Robert Hooke did all his work in the late 1600s, and in 1678 published what is now known as Hooke's law, and that is the amount of deformation of an elastic object is proportional to the force applied to deform it. In other words, if we look at the situations below, the amount that we are deforming an object is the distance that it's been changed from the unstretched amount. So in the first case, you can see it's been compressed, and we would say that is a negative x value, or a negative deformation. And in the case of stretching a spring, we would say that the x is a positive deformation. We would say it's been stretched. And so you take this Hooke's law and you look at it in terms of an equation, and we simply have that the applied force is proportional to that deformation, the amount of deformation, and then your constant value that relates those two things is k, which would be the slope of a line that I could draw if I graph this. Let me graph this and show you how that works. So if I go about and I graph it, what you're going to see if I put the applied force versus the amount of deformation on the bottom is the applied force that I exert to either compress the spring or stretch it, it's going to go up in a linear fashion. There comes a point, however, when the spring begins to deform. And when I begin to deform the spring, it's during that time that this relationship falls apart. So relationship doesn't apply anymore. So we don't look at it because we're physically changing what the spring looks like. Nonetheless, though, we can say the slope of this is k. And so if the slope of that is k, then we look at y equals mx, and the slope is k, so it's fa equals kx. And that's where we get this equation from. And so what the fa stands for is it stands for the applied force. The applied force that we're exerting on the spring. And that is a force, obviously, in newtons. The x value, as we've already said, is the amount of deformation. So it is the stretching or the compressing by a distance. So this is going to be in meters. And as I already noted, if it's compressed, it's negative. And if it's stretched, it's positive. And then we also have this k value, and that's probably the most important thing to distinguish here, because we've never really seen that here until now. The k value is the spring constant, which is really a measure of how stiff the spring is. And that's measured in units of newtons per meter. So you might want to add that, how stiff the spring is. So if it's a high spring constant, it's going to be very stiff. If it's a low spring constant, it's going to be not stiff. All right, that's all that really means. And so relatively simple way to look at that. Sometimes you'll see this put in terms, and if I just scroll up a little bit, in terms of the restoring force. Because if you think about it, this is the applied force that I exert to compress or stretch the spring. The restoring force is the force back on the ball. And if you're thinking about that, really that's because of Newton's third law. It's an equal and opposite force. So what we would sometimes see this written as is the force of the spring is negative kx. It's just the negative of what the applied force was because of equal and opposite forces. So we'll do an example of that in a minute. But I want to look back at this graph here and notice something about the area under this curve. Look at the area under this curve right here. Well, what is an area? Well, the area is, in this particular case, it's a triangle. So we're going to multiply it by a half times base times height. The base is x. The height is the applied force. I'm just going to rearrange that here. Applied force times x. Well, the applied force, hold up a second, force times a distance, that's work done. And so anytime we have work done, we know we're talking about energy, which is why we have this in terms of energy. And so if we continue to sub this in, I get 1/2 times k times x, that's what the applied force was, times x again. I get 1/2 kx squared. And so because we already said that's work being done, which is energy, we arrive at that elastic potential energy equation. And so a couple of things that we're going to define here. E with a little subscript E is elastic potential energy, and just like every other type of energy, it's measured in joules. And we've already defined K and X. Those are the same as in terms of the force. So those are really our two equations that we need to know, and sometimes we'll think about things, as I noted, in terms of the restoring force. But those are really what we need to keep straight. And the other thing that we need to keep straight is that X is negative when we compress it, and X is positive when we stretch a spring. So let's look a little bit more at this when we look at some applications here. This first example says, an applied force of 10 newtons compresses a spring by 15 centimeters. What is the spring constant? Well, let's write down our givens. Our applied force is 10 newtons. Our compression is negative 15 centimeters because it's compressed, right? So anytime we see that, we think about it in terms of negative. We need to put that in SI units, so it's negative 0.15 meters. And we're trying to find out what the spring constant K is in this particular case. And so we know that the applied force is equal to K times X. And if I sub these values in, it seems that that K would actually be a negative, but because it's compressing, that also means the applied force is negative. So K is always going to be a positive value. So in this particular case, we're going to sub these in, rearrange it to solve for K, and we're going to get the applied force divided by the X. The applied force is negative 10 newtons. The X value is negative 0.15 meters. And the K value that I arrive at, or the spring constant, is 67 newtons per meter. So we conclude, therefore, the spring constant is 67 newtons per meter. Now, I know I quickly said that the applied force was negative. Basically, the convention is this. If here's your spring, and you have something on that spring that's being compressed or stretched, if we're pushing it in, that's negative. If we're pushing it out, it's positive. So in other words, that applied force is basically saying that out from the wall is positive. And then remember that sometimes we want to put it in terms of the restoring force. And so here we said that I'm putting the applied force and pushing into the wall, which is a negative force going a negative distance because it's a compression. But the restoring force would be a positive force acting outwards from the wall, equal and opposite to that. The second example says this. Elastic potential energy of 0.35 joules is used to stretch a spring. How far will the spring be stretched if its spring constant is 66 2/3 newtons per meter? So our elastic potential energy is 0.35. It's not a lot of energy, but our spring constant also is fairly small. I know it's about the same range as what we had in the last question here. We'll keep a few extra sig digs here. So we're going to say that that spring constant is 66.667. We could keep going there. It's 6 repeated, right? Newtons per meter. And we're trying to determine how far it will go. And we know that it's positive here. Now keep in mind, energy, we could always talk about it just as far as calculating the positive value and then talk about did it compress or stretch afterwards. So it doesn't really matter about the sign here. We know that the energy is equal to 1/2 times kx squared. And we know that the elastic potential energy we know the K value we need to solve for X. So if I multiply both sides by 2, I'm going to get 2 times the elastic potential energy is equal to Kx squared. Divide both sides by K. That's going to cancel out, and then to take the square root. So it's the square root of 2 times the elastic potential energy divided by K. And so when I sub those values in, it should be relatively straightforward. We've done much more complicated questions than this. It's 2 times 0.35 joules. We're dividing it by 66.6 repeated newtons per meter. And we arrive at an answer of 0.102. Actually, 2 sig digs would be 0.10 meters. And we conclude, therefore, the spring will stretch 10 centimeters with 2 significant digits. So that's how we would do that question. So hopefully those are relatively straightforward. Let's now put this together and solve a little bit more complicated question that's going to help you more with the homework today. This third example is where the rubber hits the road. Cart 1 is rolling toward cart 2. Cart 1 has a spring. They hit, then they separate. Find the minimum separation of the carts with the given information. And so the idea is this. We've got one cart, as you can see from the given information there, it has a velocity, the second one doesn't. So it's coming towards the one with some velocity, v1. This one has v2 is 0. And it is going to be also having a spring on the front of it. And you'll notice we don't have an x value here. All we have is the length of the spring. So that length of the spring is 25 centimeters. But combined with the k value, that's going to tell us or allow us to figure out how much that string is going to compress. So the minimum separation of the carts with the given information is what we're after here. So let's see what we know. We know, let's just make note of that, minimum separation. And it might be unclear what we mean by minimum separation. So let me just help you understand that. What I don't mean, and this is because we know nothing about friction, I don't mean how far they're going to bounce off and how far they're going to end up away from each other, because in theory they're going to keep going on and on forever. What I mean by minimum separation is how close will they get when they're undergoing that elastic collision? What's the minimum distance they're going to get between them? And so you're probably thinking, hey, I know how to do conservation of energy, I know how to do conservation of momentum, and you would be right. Those are the two things that we're looking at to do here. And we're going to have to actually put these together, as we'll find one equation is not actually enough. So we'll start with looking at the conservation of energy. And we know with conservation of energy that energy is transformed from one form to another. So we need to consider all the forms that we had initially. So this is before the collision. And then we're going to look at it after the collision. Or not after it, we're actually looking at it during the collision in order for that minimum separation. So there's going to be some kinetic energy of cart 1 and of cart 2 because they're going to be colliding, and it's compressing the one, it's going to be moving the other one at the same along with it for a brief moment. And then we have this elastic potential energy that's stored up in the spring as well during that hitting of the two cars. So this is both cars moving, as I noted. And then this is the energy in the spring. And that spring is compressed. So that kinetic energy is, as we know, I can break this down here. We know this is 1/2, and we know that only the first thing has a velocity initially. So there's no V2 in that initial energy before the collision. And then we can break that down to say it's 1/2 times, if they're both moving together at that maximum compression, that's when they're going to both move together, and the one's going to fire off faster than the other. But when it's max compressed, they're moving together at the same rate. And so we're going to combine those masses like that. And then we can say this is V12 primed squared. And then we're going to add that to 1/2 kx squared. Now it's important to note here, we don't know how fast they're moving together, and we don't know this. So we don't know either of these things. We move over to our conservation of momentum. Let's look at what we get there. When we talk about momentum being conserved, we know that the momentum that we had of just the first cart is going to be the momentum of the two carts, because this is the moment that they're together before they separate off again. So they're combined. There's only the one with any momentum initially. And so, again, these are both carts mid-collision. And as we noted already, they're moving at the same speed. So we break this down. We get M1 V1 is equal to moving together, I'm going to make the total mass times V12 primed. And we know everything in this equation except for V12 primed. And so once I solve that, I can sub it back in the other equation to solve for x. So this is going to give me m1 v1 divided by m1 plus m2. m1 is 2 kilograms. So I'm going to do 2 kilograms. v1 was 3 meters per second. Forwards, we're dividing by the total mass, which is 6.0 kilograms, m1 plus m2. And this tells me the velocity after the collision, or during the collision, as the max compression occurs. And so we find here that we get 1.0 meters per second. Now, I've been pretty lackadaisical here with the vectors again, but the point is that everything's acting in this direction is positive. All right. If we have two different directions happening, that's where we need to be a little more careful. But this is definitely positive, meaning it's going to be in the forwards direction. So we come over here and we rearrange this equation for x. So this is going to give me 1/2 m1 v1 squared is equal to 1/2, or sorry, subtracting, I'm rearranging it. So I'm going to go subtract 1/2 m1 plus m2 times v12 primed squared. And that's equal to 1/2 times k times x squared. If we multiply both sides of this equation by 2, nice thing happens with the fractions. We just get those canceling out. And I arrive at a kx squared. I'm going to divide both sides by k, and I'm going to square root. So x is equal to the square root of m1 v1 squared minus m1 plus m2 v12 prime squared divided by k. So you sub those numbers in, you're given them all at the beginning of the question, and the x value ends up being 14 centimeters, or 0.14 meters that you should find. So we conclude, therefore, the minimum separation is, and we need to be careful here because it's compressed by 0.14 meters, so it's 0.25 meters. That was how long the length was, and we're subtracting that 0.14 meters from it to get a separation distance of 0.11 meters, or 11 centimeters. Now you'll notice the x value wasn't negative here, right? And that's because we're solving for energy, which is always going to give us a positive value. So don't worry about the sign, just interpret it. In this case, it's obviously a compression, so we're subtracting it from the length of the string to get that minimum separation of 0.11 meters.